With this brief introduction, let me give you the outline of the talk. So the outline of the talk is something like this, that I will explain to you the motivation behind the talk. Then I will explain to you the emerging nanoscale transistors which are already in vogue as of now. The reason I will also give you why we are going ahead with this. We will also look into what is known as a super transistor technology. And so can we replace all the current transistors by a single super transistor technology, which will be able to do all the functionality without compromising on the performance as well as area of the current chip. We will also come into the new domain, which is basically your FinFETs. FinFETs are already like about a decade old, more than a decade old, and they have been already underused for quite a long time, especially at 7 nanometer and at 3 nanometer technology nodes. We will look at what are new things, which are basically nanosheets and forksheets. So nanosheets came from IBM as well as from Purdue University, and forksheets are coming from IMEC Belgium, right? So they are still not in a very industry standard mode, but still they are at least in that mode where we can have a small discussion in an open forum. Another interesting topic which came into picture at certain point of time was negative capacitance FETs. So what you see, the brown ones are all devices, right? So this is the lowest grassroots level of SoC, right? And then we come to the next one, which is the role of artificial intelligence in semiconductor industry. Give you a brief idea about that, and then give you an idea about the emerging computing technologies. So, what researchers are looking into, industry is also looking into very actively, is one dimension is that you please look into the devices part, right? And another is the architecture on the computing parts. There are three parts to it. One is the architecture part, and the third is the computing part. So can you make some algorithms which makes our computing technologies faster? We will look into neuromorphic chips and then maybe summarize the results if time permits, of course. Right. Let's come to the motivation, right? And this motivation is coming from a database which was published in May 2015, which is basically your US National Data Defense Council. And they told us, and they gave us an idea that with 5G and 6G also coming into picture, there are about more than about 2 to 3 billion people using internet data in every day-to-day activity. Now, please understand, once you give, for every bit of data being transferred from point A to point B, you are actually spending a finite amount of energy, right? In an SoC, for example, if you look at a smartphone, a tablet SoC, the energy optimization, right, is very, very important. Which means that the battery life, since it is a fixed battery life, you need to understand one important point, that the amount of energy being transferred to transfer one bit of information from your base station, from your base, say for example, through your consumer, from your smartphone to somebody else's smartphone, right, is a direct function of the bandwidth, is also a direct function of the SoC which you are, the type of SoC which you are using, right? Fine. And secondly, its energies are very, very high. And what I wanted to show by this slide is that your requirement will be very, very high in coming days. You will have IoTs coming into picture, right? You will have these you will have IoTs coming into picture, right? You will have IoTs coming into picture, which is Internets of Things. You will have consumer electronics already much in demand. And you do have core facilities, for example, data centers, cloud computing servers. They all add up to the overall internet data which is happening on a day-to-day basis. So just to give you a small insight, nowadays for every 1 minute, you are using actually 100 to 204. It's slightly old data, but the trend is almost the same, right? And there are about 204 million emails exchanged, 5 million Google searches, you have 1.8 million Facebook's likes, and so on and so forth, right? And therefore, you have a huge data being generated, right? And if you look at the first point here, which I've written here, that the topic, the online traffic is very, very large. And these are all operated by data centers, right? So the data centers actually have a heavy traffic load. However, they do large amount of cloud computing for that matter, right? So therefore, coming to the second point, as we know, traditionally computing in our earlier days, about a decade back, 2 decades back, the computing was in-house. So it was more of at your own workstation, you're sitting and you're doing computing. Nowadays, if you look at computing, it is no more limited to a physical space, right? It is actually at a much higher level, at a much more higher level of abstraction, and that is at cloud. And that has changed the whole game plan of these computing facilities. Now, we would expect to see, and that's where the whole motivation of the talk is, that by fourth quarter of 2021, which is we are already almost entering, this data is slightly pre-COVID. So post-COVID, you can downscale it by approximately 5%. So if you look at the downscaling, it's approximately around 25 billion enhancement, right? And you see, in this cloud, in most of the cases, even in data centers, the external peripheral devices gets add-on, right? So today you have 25 billion, maybe 5 years from now, you will have about 35 billion devices being connected to the cloud, right? To maintain its proper data flow, to have a secure communication, and to also have the energy being minimized, will be a very, very important motivation for going ahead with reduced power in SoC. And that's what I was coming to in this next slide. That India alone, if you look at India, about 10 megawatt of power is consumed by data centers. So it's just India alone, right? If you look at Cisco's and Google's power, your data centers that is kept in San Jose, you will see that. So what is happening is that the amount of money you are spending in cooling a system, right, using power, using liquid helium, using liquid nitrogen, and so on and so forth, is getting more and more. But the amount of money you're spending to move your data from point A to point B is almost remaining stable, right? So beyond the point, it does not become economically stable approach to data centers, right? And that's the reason we need to work very, very effectively to reduce this amount of power dissipation in near future, because of the exponential growth of the data, right? So we are looking into several emerging devices and technologies which will give me ultra low power design applications, right? So can I just say, for example, I will give you a small example. If you look at bulk MOSFET at 180 nanometer, and then you take it up and place it in a data center, obviously it will fail, because the amount of heating it does is so large that the on-chip temperature will rise down, and as a result, the chip will actually break down beyond a particular limit. So can I replace these bulk devices by certain quasi-planar or non-planar devices, which will be able to sustain a larger current, as well as the heat signatures will be reduced drastically, right? If you use a thermal, I don't know how many of you have seen a thermal camera, but if you see a thermal camera and point it towards the IC of your computer, even your home computer or a laptop, you will see that the IC, that the CPU, right? If you put it CPU, that will appear in red. Red means very, very highly power consuming, power dissipating structure. So a large amount of research nowadays, as of today, is people are working on the methodology of actually looking at reducing these power dissipations for these technologies, right? For this ultra low power. But easier said than done, because you see, though you can, you look from the point of view of fabrication, and therefore I will come to the next slide and show it to you. See, the fabrication, silicon fabrication is a very, very expensive process, right? It's a very expensive process. Most of the fabrications, people will not like to change their fab path very easily, right? We were able to go from MOSFET to FinFET because you didn't want to have a large change in the device structure, right? And we were able to handle that very easily. Not true for other dimensions, other devices. So whenever you think about a new device, emerging device for low power applications, please keep in mind that though the physics of the device should make it a low power, but it should also have the capability to be done or to be fabricated at a low cost. The cost factor is very, very important when you're looking into the motivation for such devices to be used finally in the SoC. So let's look at the overall AI stack, because this will give you a big picture and then we'll break down the big picture into smaller ones. If you look at the big picture here, the peripheral circle, which is this one, is basically your application domain, right? These are your applications. For example, autonomous vehicle, robots, smart healthcare, smart home, smart city, so on and so forth. What is happening here, the lower periphery, is the enabler. So this is basically your technology enabler, right? So it is enabling a technology. What is enabling a technology? For example, a computer vision. Why? Because the computer vision will be used in an autonomous vehicle to guide its sensor so that there is no collision between the subsequent vehicles or subsequent vehicles. Now, therefore, within this technology enabler, this technology enabler is a computer vision. So computer vision is a concept, right? So you require to have maybe a camera, right? And then you should have a processor here, right? Within this processor, you will have an SoC, right? And within this SoC, you will have these emerging devices. You can understand, therefore, where the whole process is going into. So the whole process is going into. And therefore, you will see that most of the time, the emerging devices which you are using should be compatible. So two things which you should remember while discussing the AI stack: the compatibility issues, which means that is your emerging device compatible with the SoC, and if so, then basically the cost of development, right, of these chips, right? That needs to be taken into account. And third is performance, right? Many people take performance first and all these things later on, doesn't matter. But if you leave about the order, these three things are the most important sort of takeaways from this slide. That if you are trying to, I will give you a small example. Let us suppose if you want to reduce the delay of latency of a chip, you need to make the on currents high. One of the methods is to make the on current high. But once you make the on current high, your resistance, so let me say you want to find out the delay of a chip, right? So if you make your ion high, if you make your on current high, that will reduce your delay, right? But once you make your ion high, you know I square into R, which is basically your power dissipated, will also increase. So in a very basic fundamental term, I say that power and delay, they don't go hand in hand. They will always go opposite sense. So if the delay is lowered down by certain changes, the power actually becomes higher. Similarly, if your power goes down because of some changes, your delay actually goes up. And this is a very basic fundamental bottleneck of any VLSI chip, right? And all your emerging devices also fall in the same format. So therefore, this was the stack which I discussed with you. Now let me come therefore to the next my next part of my talk, and that is what is known as the emerging nanoscale transistors, where I can use these nanoscale transistors in the SoC, That's my final aim, right? To do that, as I discussed with you, see, I will give you a brief example. See, you see the distance between source and drain. This is my channel length, right? So my channel length is basically the distance between source and drain. And if you look very carefully, the drain current ID is directly proportional to width by length. What is the width? Width is this one. This is my width, right? So in the third dimension, which is going inside, right? Going inside your screen, right? And this is and ID is proportional to W by L, right? This is a well-known fact which you have studied in your second year BTech, first year BTech in a devices course, right? So one way is that you simply go on reducing the value of L and you will automatically get a higher value of ID, or you simply go on increasing the value of W and you will automatically get a larger value of ID. However, that's not so simple, because as you go on increasing W, you also increase the area of the chip, right? As you reduce the value of L, you're trying to bring the drain and the source together, very close to each other. And therefore, as you are aware of, Moore's law will come into picture, and there will be finally a shorting between drain and source, and the whole thing will not work. So that was the major reason why people are looking into the concept of this thing, the concept of emergent devices. Second thing is, please understand one important point, that I'm applying a gate voltage here, right? I define a subthreshold slope as the amount of gate voltage required to lower the amount of current flowing by 1 decade, right? So if you had 1 milliamp current flowing initially, and you want to make it to, so 10 to the power minus 3, sorry, 10 to the power minus 3 ampere current was flowing initially, and you want to make it 10 to the power minus 4, right? Or vice versa. Then the amount of gate voltage required is defined as my subthreshold slope. And it has been physically found out that for a bulk MOSFET, it is 60 millivolt per decade, which means that for 1 decade change in the current, I would require to have a 60 millivolt change in the gate voltage. This is what is known as a Boltzmann tyranny, which means, and I will give you an example what is the Boltzmann tyranny is all about. So you see, Boltzmann tyranny means that if you have let us say a device, then minimum gate voltage swing should be equal to 60 millivolt, right at 300 Kelvin to make it go one level down. So if you want to switch a device from it on state to off state, the minimum swing I should give is 60 millivolt. Now you see, just plug it into your SOC concept. See there, that means for device to switch off, the peak to peak voltage which I need to give for an input swing has to be, this should be actually approximately equals to 60 millivolts. Which means that if you are using a 1.2 volt supply, right? 1.2 volts basically means 60 millivolt at the top, right? And 60 millivolt at the bottom. Then out of these two 60 millivolt, only about 60. So if you're you're using 1.2, say you're using a 1. Or maybe much easier, 0.9 volts, right? 0.9 volts, which basically means about approximately 90, right? 900 millivolts, right? If you're further lowering it down, let me say 500 millivolts you're using. Out of this 500 millivolts, 60 millivolt is just gone to switch off the device, right? With other voltage, so out of 500 millivolts, right? Out of 500 millivolts, you are using 60 millivolts to switch the device. So you are left with 440 millivolts to actually drive the current and so on and so forth. So this is what is known as a Boltzmann tyranny, that my switching speeds for a bulk MOSFET cannot be lower than 60 millivolt per decade at 300 Kelvin. So what's the other way around, or what is the other way around? I will just not go into further details because these must have been taught to you earlier. But typically, if you look, it is approximately in a current MOSFET, it is approximately 80 to 120 millivolts per decade. That's it. So 60 millivolt is the theoretical limit, but the actual limit is basically 80 to 120 millivolts per decade, right? And it depends upon many factors. So how do you find it out? You take the log scale between current and gate voltage of a simple device. So this is your MOSFET, right? This is your bulk MOSFET. I think all of you are aware of. The bulk MOSFET is the source, this is your drain, and this is your intrinsic layer substrate, and the channel is formed somewhere here, right? And this is the oxide layer, which is there. This is the oxide layer, correct? And therefore, you just need to do what? Just need to draw a tangent, and in this tangent, try to find out the slope. 1 over slope will give you the value of your subthreshold slope, right? And this is a standard way of looking at how to find it out. So how do you find it out theoretically as well as experimentally? You draw the slope like this. Draw a line which is basically sort of a tangential to the slope, and then 1 upon the slope will give you the value of your subthreshold slope. Typically 80 to 120 millivolt, right? Now, so what has happened therefore is that so some of the things which have come out, which are coming out new in terms of its implementation in SOC. There are 2 or 3 important devices just come up, apart from others which I will discuss later on. One is the tunnel FET, another is the I2. This is also referred to as I2 MOS, and this is basically your NEMS. So all the domain of MEMS and NEMS is an area. I will not talk about these two, but I will talk about this tunnel FET, right? If you are aware of the fact, if you are aware of the fact that, see, in a MOS device, if you look carefully, in a bulk, if you look at the bulk MOSFET, right? The typical charge carrier is basically by drift and diffusion. So this is also referred to as a DD, or a drift diffusion transport. So whenever you are designing a bulk MOSFET and you are applying a drain bias, you increase your gate bias, and what happens is that inversion layer is formed. Because of the inversion layer, a channel is formed between source and drain. At the drain end, you apply the drain voltage, make it higher and higher, and the drain voltage and the current flows from source to drain. The electrons flow from source to drain, and therefore the ID value is from drain to source. Correct? This is what we have learned till now in our system. For the first time, what people thought of was, can we have a tunneling phenomena rather than a drift diffusion phenomena? And can we therefore reduce the subthreshold slope below 60 millivolt per decade? That was the motivation. And this was the first device which came into picture, though earlier the concept was there. In 2009, Gerhard Klimek, this was from Purdue University. No, not from Purdue. I don't remember exactly which university. Gerhard Klimek was from Purdue, but which university finally gave this idea, I am not aware of. However, this is the basic structure of a tunnel FET. So, and why did we succeed? I will give you an idea, because I didn't have to change large amount of structure of the tunnel FET. So I had this source, right? I have this drain, and I have this intrinsic layer. Correct? It is almost the same as your MOS device. So basically, this is also referred to as a pin structure, P-I-N. Why P-I-N? This is P, this is intrinsic layer, and this is your N. Right? So this is your pin layer, and this is again an oxide layer which you have here, oxide layer. I'll explain to you the concept here. Now, I will explain to you maybe the concept of tunneling before we move forward. Yes, that's a good point. I have a blank slide to explain to you. You are aware of conduction band and valence band. So I'll just give you a brief idea about that. I have a valence band here, right? Now, if you take two materials, for example, one P type and another intrinsic type, then what happens is that, so the concept here is that if there is a large population of electron here, right, or charge carriers here, and this side is empty, right? So these are all filled states, and these are all empty states. So this is your empty states, right? And these are all your filled states, and they are separated by a very small barrier, right? Energy barrier. This is not a physical barrier. Please understand, this is the energy barrier. Energy barrier. Then there's a finite probability that electrons from here can tunnel through this domain and reach to this particular point, right? So they're not drift diffusion. They're not being pulled by electric field. So they're tunneling in a quantum mechanical sense and moving towards the empty side, right? So if you remember conduction band, anything above conduction band is fully filled up, right, with large number of free electrons, and valence band is fully empty, and this is your forbidden energy gap, which you all are aware of, right? And there cannot be no energy state, at least for the silicon, within this forbidden energy gap. With this basic idea, let me come back to this again point. Let us see. So this is my p-type. So my p-type will have a higher energies compared to my n-type, right? And this is what is happening, that my p-type has got a conduction band edge here and the valence band edge here, right? And this is my intrinsic layer. So this is the barrier between the p-type. This is the barrier between the p-type and intrinsic layer. Now what is happening is, I'll just get back to this operation here. Yes, maybe I will explain this operation via this. Let me explain to you. Now let's look at ID, which is the drain current variation with respect to gate voltage, right? And let's see one by one where we are standing. So when your gate voltage is very, very low, we'll discuss about this later on. When this is very, very low, when your gate voltage is very, very low, remember energy is equals to minus Q times V, where V is the applied bias. So when you apply a positive bias, minus Q into V means this will be pushed down, right? And that is what is happening. So if you increase your voltage as compared to this, if you increase the voltage, you see this has gone down here. This one, you see, this has gone down. And therefore what has happened is the effective distance, right? The effective distance between the filled state here, the filled state here and empty states here have reduced. If you go to this point, when you have further increased the value of your gate voltage, this distance is further reduced, and therefore this distance has become so small somewhere here that you have an excessively large amount of carriers being tunneled through this point. So this is the valence band. In a p-type material, these holes are fully filled up, and in n-type material this is fully empty, and therefore separated by a very small distance here, and therefore large amount of holes will be moving from this point to this point, right? So the red color shows the probability of the tunneling. This is known as, the whole concept is known as band to band, right, tunneling, also referred to as BT, band to band, BT, band to band tunneling. So why band to band? Because you have free band, you have filled bands here. So these are filled bands, and you have empty bands here, right? Empty bands here. And you can easily transmit between these 2 points very easily, right? That's an important point. Now you see, quite interesting, I didn't do it initially, but I will just take it up now. Sorry. Is if you look, this is the energy and this is the distance. So when your gate voltage was negative, please understand, gate voltage is negative basically means that on the drain side, your gate voltage is negative primarily means, if you look at the gate voltage negative, I will just explain to you what do I mean by that. When the gate voltage is negative, this side is negative, which means that minus Q into V, when V is negative, so this is positive, and therefore, and since this is an n-type semiconductor, what happens is that these becomes very close to each other. So this is all filled state, these are all filled states here, but there's a finite probability that some of the electrons, some of the holes will transfer between these 2 points. And that's the reason your current is higher. This is also referred to as, we'll discuss that later on, ambipolar Correct. Correct. So what you have learned, what are the takeaways from all these discussion? The takeaway is by simply changing the bias of the gate and not even change the drain bias. The drain bias is almost remaining the same. I have been able to uh, change the BT tunneling probability, and I'm able to generate a large amount of current in this case, right? That is what is happening when you discuss about BT. So you see, I've given the basic difference. I have this the bulk MOSFET is the so this is the bulk MOSFET. This is the tunneling FET. In the bulk MOSFET, you form a channel, and therefore you see the green. So the blue part is the channel formation, and this green part is the charge carriers variation. Whereas in the TFET, it is the by changing the gate voltage. Here you are able to shift this barrier up and down. When you make it down, you make the effective distance lower down, and the probability of BT increases and the current increases, right? There are other types of materials also available. For example, we will have homojunctions and heterojunctions. For example, you can have, for example, all silicon. So this is silicon, but heterojunction will have germanium, silicon, and silicon. Why germanium is used? Because germanium has got a relatively higher mobility of charge carriers, and therefore you will have a larger current in this case, right? Not only that, a p-type germanium and intrinsic silicon, if you look carefully, has got a very small distance to travel as compared to this one, right? It's got a very small distance to travel, which means that the effective tunneling distance between source and channel is very low in case of heterojunction. Just to give you a brief idea, in 2010, I think 2010, yes, in VLSI design conference, in VLSI symposium, I suppose, the first application of it was given, and you see the subthreshold slope was given as 46 millivolts per decade. Effective gate length was around 20 microns. So in tunnel FET, one additional advantage is that you don't worry about the channel length, right? You are more worried about the subthreshold slope in a sense, and that is about 46 millivolts per decade. The value which we are actually expecting to see, right? And this is basically a nickel. So this is basically, if you look, this is basically what is known as a nickel silicide junction, and this is basically a Schottky barrier. So a very steep function. So when you have a very steep functions, your dimensions reduce, and you can have very large BT. Right? Other experimental TFET, CNT, was used by Stanford way back in 2006. It didn't work very well. Strained germanium double gate was used, and it was either giving you a high current and a good SS. Hitachi in 2010 gave a novel TFET device, and then in Peking University gave a novel TFET device made of silicon. And finally, around Hokkaido University in Japan, they made a 3.5 semiconductor, indium arsenide nanowire. Don't worry about what this nanowire is all about, but the base material was indium arsenide, and they received a very good, that was very important and interesting. They received a subthreshold slope of 20 millivolts per decade. So your switching speeds are very fast in this case. So you can use it for all high frequency applications, wherever your switching speeds are very high, right? And that is where you need to put your next efforts as far as tunnel FET is concerned. So let me summarize TFET, and we'll go to the next topic after this. In TFET, therefore, what we have learned that its benefits are, it's got a very steep subthreshold slope. It's even smaller than 60 millivolt per decade. One advantage is high ion by ion means when the device is in the on state, the amount of current carried by the device. Sorry, amount of current carried by the device is referred to as ion, right? And what is I off? I off is when the currents, when the device is in the off state, then we define that to be as the off current. Now, so this is basically, your off currents are relatively very small, right? And the reason is the leakage currents are very low in a tunnel phase. However, this increase in the ion, so when I say ion by I of ratios, I say ion by I of, right? If you look at these ratios, this I am saying is very large, right? This is large ion by I of ratio, correct? Now, this enhancement in the ratio is not because of high ion, but a lower I of. The leakage currents are low, and that is also one of the slightly offside of this tunnel fed, that its on currents are not as high as expected because it is based on BT and not on drift diffusion. Correct? Right. Scaling is very easy, so you can actually scale up your device. You don't have to follow Moore's law as such, and you can actually use silicon germanium, silicon CMOS processes. However, what are the challenges? Even ambipolar current. Ambipolar currents are the reverse currents. So you see, I will give you an example. If you increase the drain voltage, drain bias, then this will go down, right? And there will be a current which will be moving in the opposite direction in this side. This is known as the ambipolar current. Correct? So that this is a major problem of devices, that it's an ambipolar current which comes into picture, right? You don't have, the third thing is just like in NMOSes, you have an NMOS and PMOS. Typically, making a P-TFET is very difficult as compared to an N-TFET. So people don't generally have this CMOS process, compatible process in this case, right? They are very good at lower voltages, but they are not very good at relatively high voltages, and that's a major problem area which people are facing, that you cannot use it for power devices or power electronics purposes for automotive industry. Right, so we have finished with the one basic idea about transistors. Let me come to the concept of super transistor technology. And shall I, Professor Raut?
Yes, sir.
Shall I wait for questions now, or at the end of that whole discussion we can have the question?
That will better at the end of your session, sir.
Right.
Yes, actually.
So I will take about more. I will take more about 40 minutes maybe, right? 45 minutes.
Yeah, so it will going to stop at 11:30 your session. So 5 minutes before you can close
Sure.
Then 5 minutes you can take for the questions.
Correct.
Yeah. Thank you,
Okay.
sir. Yeah.
Thank you. Okay. So now we will have a super transistor technology. I'll just give you an idea about the super transistor technology, which is already within our domain, coming up in a big way, but it will come up in coming years. A very good amount of research is going on in this area. So I will just, you don't have to worry from where I got this equation here. Which equation? This equation. This is dVg d psi s multiplied by d psi s d log of id. D log of id, you understand, is the log scale of current, and this is the change in the gate voltage. What is this? This psi s is referred to as surface potential, right? I'll explain to you what surface potential is, maybe from the MOSFET diagram which I had already shown you. Yes, if you look at this MOSFET diagram here, then see, if you apply gate voltage here, some say 1 volt, there will be some IR drop here, some across the oxide there will be some drop, and therefore the amount of voltage visible at silicon dioxide. So voltage, right, at silicon dioxide is referred to as surface potential psi s. Right? So not all the voltage, not all the gate voltage appears here. So 1 volt will appear as say 0.5 volt here. Right? And this will go on varying from drain to source, because in most cases source is generally grounded, right? And drain is applied a positive bias. So this value will go on increasing as you move from source to drain. Here it will be approximately equals to 0. Here will be approximately equals to VD. But you understand the concept of surface potential now. So with this knowledge, let me explain to you what the surface potential is all about. No? So you see, if you look, so this term is M, and this term is N. So this tells, the first term M tells me that if I vary VGS, right, then how does my surface potential vary, or vice versa, that if my surface potential varies, how does my VG vary? But since VG is a bias which is given by the user, so dVG dψs is basically the amount of variation in the surface potential because of the variation in the gate voltage. And what is dψs d log of ID is basically the change in the surface potential because of the change in the current. So or vice versa. If I change the current by one log scale, then how does my surface potential has to change in order to sustain this much amount of current, and that is equals to M into V, right? Now, if you look at this M value, right, you see your dψs, right, will always be less than dVG, and therefore M is always greater than 1 for a bulk MOSFET. And N is basically this N value is limited to 60 millivolt per decade. So for every 1 decade change in the current, you will have a minimum 60 millivolt. This is the Boltzmann tyranny which I talked about. So if you multiply, so if this is 2 into 60 will be equals to 120 millivolt per decade. So 120 millivolt per decade will be the SS, right? So this is how we calculate it, right? Now I will go one by one. So my main aim is to reduce this SS to below 60, right? That's my whole aim. So I can do that by two things. If I'm able to make this M less than 1, that will make my clear. So even if my dψs d log of ID is 60, if my M is 0.5, I will get SS to be equals to 30 millivolts per decade. Correct? So let's see how we can get ahead. So this is the sort of a super transistor network which is shown here, and this is on the x-axis. On the first quadrant, we have this MOSFET. We have already discussed M is greater than 1, N is greater than 60, and therefore if you multiply these two together, my SS is always greater than 60 millivolts per decade. Let's come to the left hand side because we just now finished TFET. In this case, M is also greater than 1, but obvious because you are not going to change the surface potential being less than VG, and therefore M is greater. But what has happened in this case is that N has become less than 60. N has become less than 60, which means that the product, there might be a finite probability that M into N might be less than 60 millivolts per decade. Let's come to the third quadrant, which is your NC FET, negative capacitance FET. This is quite an interesting phenomena. And what happened in this case is that somehow or other, if I apply a gate voltage, say 1 volt, and I get a surface potential of 1.5 volts, which means my surface potential is getting amplified. My surface potential is getting amplified, then my M will be less than 1. And even if my N is equals to 60, in an NC FET, NC means negative capacitance FET, which was actually invented by Syed Salahuddin and Professor Shukri Datta in 2008. This NC FET will have an SS which is much smaller than 60 millivolt per decade. Right? And then if you look at NC TFET, means I marry the good idea about negative capacitance plus tunnel FET. Then I get in that case M less than 1 and N less than 60. So if you want to achieve the best amount of subthreshold slope, the device to look into is the third quadrant device. Also, this is also referred to as a third QD, or third quadrant device, which is your NC TFET, right? M is less than 1 and N is less than equals to less than 60 actually. Okay. So this is the basic concept of a super transistor. So you see, these are all about a decade-old concepts. If you look at NC FET, it is about 1 decade old, 13 years old. If you look at TFET, TFET was quite old, about 2 decades old. MOSFET you're aware of is anybody can understand what is the MOSFET? When was it first invented? It was given by a patent in 1925 or 27 by Lilienfeld. This was the person who filed the patent for the concept of the FET device, right? For all the FET devices, right? The field effect transistor concept was given by Lilienfeld, 1925. Correct. With this, let me come to therefore the super transistor technology, which is the second part of our talk, and that is what we do. Therefore, is it is exactly like a pin structure. So I've got a PIN. So this is my P, this is my I, and this is my N. And then what I do is I have this gate, I have this oxide, which is the blue color. But what I do is I add a layer of ferroelectric material. Right? This is known as a ferroelectric material. Ferroelectric material shows the concept of polarization. Right? Shows the concept of polarization. What is the meaning of polarization? And I think all of you are aware of what is polarization. Polarization basically means that you have in a ferroelectric material, you have these dipoles, right? You have these dipoles. Now, if you apply electric field in this direction, so this is positive, this is negative, what will happen is these all positive will be aligned towards this side, all will be aligned towards this side. So if you switch your electric field, these dipoles will also start switching. Right? When the dipole switches, what does it actually do is that when the dipole switches, it tries to have a voltage developed across the two edges of the ferroelectric material. Correct? Right? And that is quite important, that the two edges of the material will actually see a change in the voltage because of the change in the polarization of these dipole moments, right? And that is what we are trying to show you here. So what we did was we tried to just take the ferroelectric capacitor and into something like this. So I have a gate structure here. I have a gate. Then I have a, let us say, an oxide, and then I have a ferroelectric, and then the same structure, PIN. What it has done is, and I'm not going to physics of it detail, but what it has done is that by inserting a ferroelectric material inside, we were able to amplify this value of psi s. Right? Because so what has happened is that whatever voltage you are giving from the gate side, it is getting amplified and it is being shown on the channel side, right? So by putting the good features of TFET and NC, we were able to have a super steep subthreshold FET known as NC TFET, right? And it's very, very low NC TFET. Methodology people adopted was that if you replace it, let us suppose you replace the oxide layer by a hafnium oxide, right? Which is a high K dielectric. Then also you will have an amplification of the surface potential, right? So these are some of the techniques by which you can improve the surface potential. Once you do that, you make the energy efficiency much better because you are able to achieve the same value of ion with a much lower value of Vg, right? And therefore it is becoming more energy efficient, approximately 10 to 15 times more energy efficient as compared to a bulk MOSFET, right? So just to give you a hint where these SOC devices or these, so that takes, I think I finished with TFETs. I will explain to you what TFETs are. I will explain to you what super TFETs will be in terms of NC TFETs. Now we'll go for a bigger picture, just above the devices, and show to you other devices which are actually into the system. And Some of it is shown in front of you. So if you look at Intel, they had this 14 nanometer FinFET tri-gate structure for a long period of time. TSMC are currently working at 3 nanometer FinFET, and as well as they're working extensively on 2 nanometer GAA devices. Similarly, if you look at GF, they are working at 14 nanometer. So 14 nanometer FinFET and even 7 nanometer FinFETs are all well stabilized. Next thing to look into is 3 nanometer FinFETs and other GAA devices. GAA means gate all around devices, right? And they are well within use currently in most of the technologies as far as consumer electronics is concerned. Maybe I can show you the next slide. Yes, this is okay. I'll show you. So you look at the first slide here. I have taken it from IEEE Spectrum magazine, and it has come very recently, about 1 year back. If you look at this is your bulk device. So this is your bulk MOSFET, which we have been already studying for past from your. So you're working on bulk MOSFET for past large number of classes in your BTech. So you know that you will have a source. This is your source, right? This is your drain. This is your gate, and this is a channel, a substrate through which the current flows. 2011, 2012 was the time till which your bulk MOSFET worked very fine, and nobody used to raise the question on that. Post that, we enter into what is known as a FinFET. FinFET is something. The structure is something like this. You will have this. You have this silicon. So the gate is surrounding the silicon in all the 3 directions, and you apply a gate voltage here. So there will be a channel which will be formed here, and this is source and this is drain. And if you apply a drain bias, there will be a current flowing through the device. So it's a better gate control and a reduced leakage, right? So these are the 2 primary advantages of a FinFET. That the gate control is much better in this case because it is surrounding it in all the 3 directions, and the leakage currents are very, very low because the very structure allows you to do that. We'll not go into details on this one. What has worked, and for the last 2 to 3 years people are shifting onto it, is what is known as a stacked nanosheet FET, right? Stacked nanosheet FET. You see, if you look here, these ash color or brown color, whatever you want to say, are sheets of transistor which is moving parallelly with respect to each other, and it is surrounded by all the 4 sides by a gate. So this is basically a sort of a GAA structure. Right, so basically a GAA structure. Why? Because the gate is surrounding this device in all the 4 directions, right? No, it's surround gate structure. This is basically the concept of nanosheet. So as a rule of thumb, your second order effects, right? For example, Dibble, threshold voltage, roll-offs, everything, second order effects will be minimized, right? When gate has a better control over the channel. Control over channel. So better the gate surrounds the channel, right? Better will be your, lower will be your second order effects. It will be minimized drastically. Correct? And therefore you see your GA structure or the stacked nanosheet structure will have a much smaller value. So how do you fab it? How do you fabricate it? It's very simple. You take, say for example, you take silicon germanium stacked layer here, right? And then you etch away using certain chemical etching. You can etch away germanium. Silicon is revealed, and then you take the gate dielectric material, which is basically your oxide layer, using ALD, put it over your silicon layer, and then wrap it around with metal gate. This is your metal gate. So it completely surrounds the channel region in a much more easier fashion, right? So you have, but these techniques are well-defined techniques, and you don't have to make a large change in the technique in order to achieve these changes here, right? This is a TEM, transmission electron micrograph picture of the nanosheet which you see. And if you see, these are your nanosheets actually. If you look very carefully, these are your nanosheets here, right? These are your nanosheets. This is the gate which you see. This is the gate, right? And these are your nanosheets. And this is your metal gate which is surrounding. This is your substrate. Right? And so you have a layer of gate which is surrounding. So there are many issues in nanosheets. I will not go into details of that because time is limited. But the overall picture it tells me is that it gives you an idea about how a nanosheet actually works. It gives you an idea about how a nanosheet actually looks into it. Another concept which has come into picture is, see, the problem is, if you remember, the problem is, just hold on a minute, there is some disturbance in the some water is dropping, so I think you will be getting some noise. I will try to remove that and get back. Give me just 2 minutes. Sorry. Meeting. So, okay, thanks a lot. Sorry for small change because of we're trying to repair it. So the problem is, see, that for all your devices to be made or to be actually done, the N MOSFET and P MOSFET sign. So for every N MOSFET or P MOSFET, so type and bring it to right. For every N MOSFET and P MOSFET, you require to have these on-chip formation of this N MOSFET and P MOSFET, right? And that gave what is known as a fork sheet. So fork sheet, if you see this, we cannot open the whole because it's still it's still under patent to be filed. So we have one N MOSFET here and a P MOSFET here. So both NP, you will have both N and P on the same chip, on the same substrate. So your area will be relatively small. So your nanosheet has come from IMEC and Purdue. Not IMEC, IBM. They were the first one, and then Samsung is also working on it, on nanosheets. And Fox Sheets, IMEC Belgium is working on it, and still Fox Sheet is still under this thing, right? I will not go into details of the Fox Sheet process, but if you want, I can send you these details later on after the FDP is over. And if you want to read more on Fox Sheet, these are the few papers where you can actually have a look. These 2 papers came out, and these are in open domain papers. One was by Rayagada and another was by White. And these 2 are actually working at sub 5, sub 2 nanometer devices. And these are all Fox Sheet devices which is there. And they are much, and this is actually published in IEDM in 2019. So you can see already 2 years have passed, and people are quite ahead in this domain. And these 2 papers will help you to actually understand the properties of the device in a much more detailed manner, right? So I've given a brief idea about the emerging device technology in the, and other aspects of it. Now, in the next about 15 to 20 minutes, I will take care of certain negative capacitance FETs and give you an idea. Already I discussed with you NC FETs, but I'll not go into details of this one, but I'll just show you one small application of NC FET. I'll just show you one small application of NC FET, and then we can close. We can go to other part of it. You see, this was what has been done at by my research scholar, who is working on organic ferroelectrics, this is also known as organic OFEGS, means organic ferroelectric gate stack. So this is basically, if you look at the, so you have two polysilicon gates, right, which are there, and they're separated by ferroelectric material. This is an organic ferroelectric material, right? And this organic ferroelectric material, as you can see here, is being replaced by equivalent circuit model, showing it as a variable capacitance and a resistive element having a organic ferroelectric material, right? And so the work which we did while doing all these this job was, can we have organic ferroelectric material which is compatible with silicon, and we can achieve higher switching speeds, right, as compared to your bulk MOSFET or even FinFETs or even nanosheets FETs. And we worked on it and we got some interesting results. So this was so you see, this is the negative capacitance region, this one. So you see, as you increase the voltages, your polarization increases in this region and in this region, right? This and this region. But this is the region where if you reduce your gate voltage, the polarization increases. So that is what is known as the negative capacitance region, right? And need not worry about what is written on the left hand side. That's a mathematical equation steps which people solve for ferroelectric material, and people are working on it in a much more detailed manner. So we did a simulation as well as experimental data, and we got some interesting results. I'll just come to the final results maybe. I'll not give you details of this one. I'll just show you the basic. So yes, the basic idea was that using this device, the proposed device, also referred to as a Landau transistor, we were able to achieve a minimum subthreshold slope of 38.21 millivolts, right, at VD equals to 0.7, right? So this was sort of a super transistor which we are looking into, and whose subthreshold slopes are very, very low. It's about 38. Now, if you further lower the temperature, this will go down to a much lower value, right? And this is a 16 nanometer process flow, and gives a better scale as far as working switching speeds are concerned. So I just will not go into details. We'll skip this slide for the want of time. But primarily using such techniques, you will be able to achieve a reduction in the value of your subthreshold slopes without compromising on the performance limitations of the system, right? Okay, I thought maybe I'll just give you a brief idea, because maybe later on you can have a look into it. I will not go into details of this one. I thought of giving you an idea of those who would pursue research. But let me give you a brief idea about what is the role of AI in semiconductor industry, right? And that's because it's coming up in a big way, and this is a faculty development program. I thought of maybe giving you an idea about where you as a faculty can actually contribute in terms of upcoming semiconductor industry domain area. So if you look very carefully, we are going from the bottommost, which is basically your on-chip, to almost a system level and application level approach, right? So if you go from CMOS technology, follow the light blue curve, then the first thing which comes into devices, which we have been actually doing it for the last 1 hour or so, explaining to you, right? And within that, you will have For example, if you look at new technologies like the tunnel FETs, right? FE FETs, FinFETs, and so on and so forth. These are there. And the process nodes which we are talking about is around 5 nanometer, 7 nanometer, and 16 nanometer. This is what we're looking into. If you go slightly on the higher side and look at your chip level design, then using these technologies, people have been trying to do memory stirs, in-memory computing, analog computing for technology, STT-MRAMs, right? Looking at high-speed GDDR transceiver. There is a good amount of work being done at SerDes and serializer and deserializer for the purpose of 5G applications. Similarly, if you come to algorithm space, then there is a large amount of work being done in neural networks, deep neural networks, neural network algorithms, and machine learning algorithms using support vector machine concepts, right? And finally, you need to map it to the application domain, which is basically your image processing or video processing, sound and speech processing, natural language processing, and also in terms of drone technology in controlling, right, and data control and so on and so forth. Please keep in mind that these are all so the blue curve shows you that what is driven by theoretical innovation, and the green curves gives you an idea about application requirement, right? And these are the few of the application requirement you as a faculty can actually look into. Before moving further, maybe I can, I don't know, maybe I can just small thing for those people who are actually trying to do, will enter into their research. This just, so I will end my talk with this 10-minute slide on how to, are you ready? So those people who are trying to do their research, or even those who have done their research, and those in the senior positions. So if you look at the x-axis, this is the, I've taken it from a website, this whole data. And if you look at the grad students' motivation level versus the year, you will see that it's almost like a sinusoidal curve. So his motivation goes down, goes up, goes down, goes up, goes down, and so on and so forth. It's a regular up and down feature which is there. If you look finally, then at various points, you will. So what will happen is when you will enter into PhD, you are very, very anxious, enthusiastic. You discuss with your advisor. Then you will see that okay, it's okay, it's good to be good, but then you are not the best because your lab mates are better than you. Then your advisor will tell you, no, you should work very hard. He will encourage you, and your motivation level goes high, right? So somewhere around first and second year of your PhD, your lab mates will have n number of papers. You will not be having n number of papers, and then you will have some problems, and so on and so forth. And so this goes on like this, and finally you end up having if not a very low motivation, but just a fun. This is just a fun slide. Don't take it very strongly, but you see that your jobs, at least in India, your job outlook is not very, very strong. It's rather weak, and so on and so forth. So some key questions if you want to do a research is, first of all, are you passionate about it, right? Are you passionate about doing research? If you are not, please don't enter into this region, because this requires a lot of frustration. This will have a lot of frustration. There will be large amount of pitfalls. There will be many rejections. So you see, when one of your colleagues told us that Professor Dasgupta has 250 papers which has been accepted, please also know that beyond those 250 accepted papers, there were a large number of rejections also. So maybe there were 600 or 700 rejections. Then only I was able to get 250 number of papers, and all because of my research scholars and my staff working in this domain. So first thing is, are you passionate enough to do a research, right? That is how go ahead. So some of the key questions is therefore, so how do you do a scientific research, right? So there is no one word answer to it. It is basically passion driven, right? It is basically passion driven, and there is no other way to go about it. Second thing is, publishing is important, because you want to disseminate your information to the external world. But please understand, is it the only important part? No. Publication is an outcome, right, of a good work which you have done. You should not run after the publication. Publication will run after you, provided you are able to do a very good work, right? So it is not, publication is important, but not sacrosanct. So I have seen a thesis of IIT Kanpur of just 32 pages without any publication, but that is one of the most highly cited thesis within the IIT Kanpur domain, right? And so only having large amount of publication is not important, but having large amount of understanding is very, very important, right? That is very, very important as far as publication is concerned. Just a minute. Right. Right. So yes. Once you have understood that what is the requirement, you should know how to plan your thesis. So what will be the parts of your chapter of your thesis? You should sit with your advisor, get it done. Then how to manage a project. So you're given a work by your supervisor, break it into small pieces, right? And have a timeline associated with it. You might not be able to meet those timelines, so have timelines. Have also the deliverables being discussed with your advisor. Have those timelines being put into position. Try to achieve those timelines. You might not be able to achieve, which is part and parcel of research, but then try to change your deliverables as well within the project, right? And then how the results will be assessed. So how will you assess it? Your advisor will assess it. Your advisor will initially assess it. After this, you will have a peer review of your paper, of your work. And those who are working in so there are people who work in experimental domain, people working in theoretical domain. They have their different approaches to research, but generally research is passion driven. You please keep this in mind and move forward as far as research is concerned. So I think I can skip this. Depends on various places and various. So you do a background search initially. You do a background search and do what is the state of the art, what are the research challenges which you face, and therefore you present a SOA and work plan, right? And then you start working on your thesis. Look at the doctoral conferences. You disseminate it to a wider domain, and then after disseminating it, you also do a thesis preparation, and then you submit your thesis later on, right? You also have another important point is coming up in recent years, about 10 years back, is IPR issues, right? So many of the research are now getting into applied domain, right? And at least in engineering, right? And therefore, there will be much clash with IPR, which is your patent rights. So you should be also aware of these patent rights, and I would request all the functionaries of institutes to have these patent offices, which patent and plagiarism. So these two are important as far as in research, patent and plagiarism, right? These means sensitizing people, which is the job of the university. Sensitizing your research scholars, your faculty members in the domain of patent applications and plagiarism is a very, very important part, right? And that's quite an interesting issue, which has opened up a large amount of research in this domain. Career opportunities: you can do a postdoc, you can be a professor at a certain institute, you can do publishing, you can also enter into government policy making process. For example, a scientist in MIT or in CSIR labs, work into other options. You can do consulting and so on and so forth, right? And so these are the few areas which I thought. I'll just finish my slides by giving you a small, maybe one small. I'll just give you, yes. I'll just give you one small thing and I'll close the topic within the next 5 minutes. See, I don't know how many of you must be aware of your von Neumann architecture, Harvard architecture. and all those architectures of computer architecture, which is people will talk. Now, initially, if you remember, it was you had a memory block, you had an AI processor, and the data was shifting from. And so, whenever you want to have the data, you take it from the memory block, and the AI processor was able to, not the AI, the processor was able to process the data, send it back to memory. Memory had I/O, and you were able to display it in the I/O or store it in a I/O, store it in a memory location. Now, what has happened is with this such a vast increase in the data density, your bus, which was carrying this data, is now becoming the bottleneck. The bus is not able to take such a large amount of data from memory to the processor and vice versa, right? And that's what is known as a von Neumann bottleneck, right? And these are the challenges which people face. So if you, so the idea was, I don't know, I don't have a picture here, but the idea here is that if you can have the computation done in the memory itself, right? What is known as computed memory, CIM processes, then you will be saving a large amount of this. So this bus will not come into picture, right? And this is one of the major technology challenges happening in the current AI scheme of things, where you want to have the memory and the processor on the same platform, on the same chip, right? Not on the same chip, but the memory at one time will behave like a memory, and another time it will behave like a processor. So these are the few areas where you as a researcher or you as a faculty can, or you as a student can work on in coming days, right? And so these are the few technologies. I think I will stop here. I don't have the overall slide, but just to give you one last slide where we are moving forward. We are now looking into combination of SoC and SiP. That's what I wanted to end my slide with. That currently SoC and silicon in package, SiP, right? So you will have large amount of biochips, like high voltage power devices for automobiles, sensor actuators, and all these things will be there. You have to merge that with the SoC, which is basically a digital application or mixed signal applications. With reduced timelines, you also have to look in reduced technology nodes. You have to also look beyond CMOS. So we are now currently looking into, say, organic, for example, I gave you an idea about organic ferroelectrics and so on and so forth. So these are the future roadmap of electronic industry. With this, I think I will stop here, and I will just stop with this slide. And we are looking into beyond more drastically, and I'm now open to any questions. Anybody wants to ask a question or discuss?
Sir. Thank you very much,
Hello.
sir.
Sir, I have a doubt, sir.
Please.
Sir, there are many directions for the future VLSI, but the major problem I encountered is the tools are very costly, sir. Is there any open source research into VLSI tools?
So there are no, to the best of my knowledge, there are no open source TCAD tools, but there are open source EDA tools. Say, for example, I know eSIM is there, eSIM. Then you have LT Spice is there, which is basically Bombay, IIT Bombay. You have also Magic, which is basically a layout from IIT Bombay, right? So these tools are open domain tools.
Yes, sir. Yes. But is there a scope for research in the tools, sir? In the CAD tools?
Yes. There are a large number of people who are working in this domain of large EDA. So optimizing of EDA, and optimizing your the algorithms, backend algorithms for the EDA, right? That is where a good amount of research is going on. I will give you an example. So convergence rate of an EDA tool is a big problem still today. So you cannot converge very fast. If you can't converge very fast, the time taken for simulations to end will be very large, right? So a good amount of research is working on the EDA part of it, that EDA part of it. Second part is basically you're applying machine learning techniques in the EDA, which is still not there. In most of the semiconductor tools, they are not there. There you can do a large amount of contribution.
Okay, sir. Thank you. Thank you for the information.
Okay.
Sir, good morning, sir.
Yes, please.
Thank you so much for your wonderful session, sir. Sir, one doubt I am having, sir, regarding the stacked channel. How the charges will distribute, sir? How the physics will be behind? Because if some 3 or 4 channels are there, means when we see that it looks identical, all the channels will be identical. Will there be any difference?
No. From a look wise, they look like identical. In reality, they are not. They are in fact. So if you look, so any channel which is close, as you go at the top direction, right?
Okay, sir.
It is much closer to the gate stack.
Okay, sir.
So they have a better control. You have a better charge carrying capacity. As you go down deep inside the stack in the nanosheet, the charge formation becomes a bit weaker. So though they look exactly the same, but the behavior is quite different. So this is for the DC. For AC, if you look very carefully, these nanosheets are all like they are one stacked over another. So there will be intersheet capacitances also.
Okay.
And these capacitance will lower your output frequency. So we are still working on it. People are still working on it, but we are not very sure where we will end up. But as you rightly pointed out, many work has to be done in this case.
Okay. So while if you are mathematically modeling, means we have to consider this effects and all that.
Correct. For example, capacitance effect. So you have to solve the Poisson equation in a proper manner, and the boundary conditions will be changing, right? And therefore the current carrying capacity will change for each of the stacked nanosheet which you have there.
Okay, sir. Next question. In the NC-FET, actually it's a kind of a new device.
Correct.
So how? What are all the things we have to concentrate, sir? If you want to work on that, what are all the?
So first of all, you need to work on the concept of polarization. So you need to understand the ferroelectrics properly, ferroelectric domain, because in the ferroelectric domain you do have this problem of polarization, right? Which means so once you polarize the particle in a certain direction, the applied voltage gets added up, and therefore you see an amplification in the voltage, and therefore the on current increases. So the problem which we are facing in TFET to an extent was removed in NC-FET, and that was working very fine till even today. But the problem with NC-FET is that they have an issue with respect to fabrication, because making a ferroelectric layer in a very fine manner over the oxide layer, fabrication wise, is slightly a difficult issue in terms of this thing. Second thing is that it also destroys the silicon dioxide interface, right? And these are the few challenges of this thing. But to understand NC-FET, you need to very well understand ferroelectrics, understand the concept of negative capacitance from ferroelectrics, and then bulk MOSFET for sure.
Okay. So this kind of NC-FET will be used for the future computing techniques like
yes. So for all your sim, so the problem with TFET was low on current, right? And therefore this NC TFET was actually able to remove that very easily. Now they are in use currently, but its assimilation into the real world is still not done in a proper manner. It is still pending. So that's where you can actually work on drastically.
So real-time device is not yet emerged?
No, as of yet, to the best of my knowledge, not many places this has been used till now. because of power issues and because of compatibility issues with ferroelectrics.
Okay, sir. Okay, sir. Thank you so much, sir.
Thank you.
Sir, good morning, sir.
Good morning.
Sir, may this particular issue be applicable in space applications, sir?
No, space, you see, you need to have a rad-hard design, radiation hardened design. For
Yes,
space
sir.
application, you require to have so there are certain, so for example, ISRO, or for that matter, your European Space Agency or NASA, they have these standard set, right? And you have to make those devices pass through these standards. Then only your device is space radiation compatible. You getting my point? Right.
Yes, sir.
So NCFET as of today is, people have not studied its radiation effect too much, and it's still an open domain study which people are there, right? It is still an open domain research area. So I'm not so sure where it will be finally used, but that's an area where you can actually look into. Yes.
Okay, sir. Okay. Thank you, sir.
Thank you.
Any questions from the participants? Okay, I think there is no questions. Thank you very much, sir, for the particular application point of view, semiconductor system on chip applications and relate to the particular industry. So I am very much thankful to you, sir, for the importance of your time and talk and relating to the particular semiconductor parts to the academic as well as the industry. So thanks again, sir.
Thank you. Thank you.
Yes, sir. Thank you, sir.
So can I leave now?
Yes, sir. I will connect after that. Thank you, sir.
Okay, thanks a lot. Thanks all of you for a patient hearing.
Thank you, sir.